Good afternoon, everyone. My name is Haesun Kim, and this is my colleague Gihwan Kwon. We are from the Boeing company, and today we are presenting introduction and consideration of temporal partitioning in avionics with open source ecosystem. All right, let me explain what we are going to talk about today. And first, I thought that while many of you are here are familiar with open source, but you might still feel a bit distant from aviation software or avionics. So to utilize and apply the open source ecosystem in avionics, you need to understand the aviation system. So I'll spend some time to explain it. And following that, we discuss where and how open source can be applied. In particular, we are cover temporal partitioning, which is essential for the integrated modular avionics. Finally, we will conclude this presentation with future work and the collaboration with open source communities. Yeah, first, I'm going to explain the motivation behind ARINC 653. So before we delve into what ARINC 653 is, we need to some background on IMA, so I've added this slide. This diagram compares traditional federate architecture on the left and with IMA architecture on the right. In the traditional federate approach, each function such as flight control, flight management, and controls and displays runs on its own dedicated line replacement unit. And each box has dedicated hardware, wiring, and certification artifacts. This is simple isolation, but increases weight, power, maintenance complexity, and certification cost. So redundancy often means duplicating whole units, and upgrades are slow because each module is independently qualified. On the other hand, IMA consolidates multiple functions on a common computing platform, which strict time and space partitioning. Safety critical and non-critical applications share processors through a certified partitioning kernel, allowing resource sharing, reduced wiring, and easier incremental upgrade. So how does IMA architecture fit with ARINC 653? So IMA targets several clear design objectives. It must preserve functional performance and operational safety while consolidating our functions. It aims to minimize cost of ownership through reduced size, weight, power, wiring, and easier maintenance. And IMA requires integrated partitioned function software, so multiple functions can be shared common hardware. It supports loadable onboard software and modularity to enable upgrades and reuse. So it provides fault tolerance and transparent health status reporting for predictable recovery. Finally, IMA needs a standard interface to handle hardware dissimilarity across vendors and platforms. So ARINC 653 is essential because it delivers a standardized application software environment and enables safety consolidation, modular upgrades, and fault containment, and cross-platform interoperability, exactly the capability IMA requires to be practical and certifiable. Now, let's find out what ARINC 653 is. So it is an aviation industry standard. So the primary purpose is to define an application program interface and associate operating environment primary for applications targeted to IMA architecture. So it is also called it as APEX, Application Executive. For my benefit, I will call them for both ways during the presentation. The main object of 653 is to support for the embedded software up to software level A, which is the highest one. And among multiple applications with different vendors, the level of safety criticality is identified, and they are classified and isolated within a particular partition. And an application using the Apex API will be portable to another platform operating system which supports Apex. So ARINC 6x3 consists of Part 0 through Part 5. Part 0 overview. Part 1 and Part 2 are required services and extended services. So for Part 1, it describes a general partition, process, time, memory management, APIs, and the communication method between processes and between the partitions, and health monitoring API as well. For Part 2, there are some extensions of Part 1 system functionality, and Part 3, the conformity test specification for the services that I mentioned before. And Part 4, subset services, and Part 5, core software recommended capabilities. Actually, it addresses the limitation by defining the core software capability. So how does it look like? The left one is the conceptual diagram for the module architecture specified in Part 0. From the top, applications, Apex services, operating systems supporting the ARINC Apex service, and platform hardware. It assumes the partitioning exists, and as you can see at number 2, the Apex main task is to define the API layer and associated behavior. So to define Apex, it would be collaborate with operating system level functionality like scheduling, exception handling, and health monitoring. So the core module could be the one, and it would be updated partially depending on what the existing operating system supported. It needs to define a specific two-tier scheduling to meet the requirement. So we'll talk about it later. And on the right, it shows one example of API in Part 1. I picked create process. So upon the general explanation of process measurement functionality and the signature of API and the definition of API behavior come after. And this includes the error handling as well. So the declaration is released as a header file, ARINC 6x3.h. Let's think about how application works using the Apex API. There is a partition, the red boxes, and there is a partition that has its own period, duration, and memory requirement. And within a partition, an application will have periodic processes and aperiodic processes. It can be created by the process management API with the process attribute. So as you can see, the attributes include processing rate, duration, and priority, and state. The processes might need to communicate with other process outside of our current partition. In the case, it can be done by inter-partition communication. Inter-partition communication API has the port attribute. So depending on the data to be communicated, we can decide which type of port is created. And then health monitoring process will check the health within our partition and report or log it to the outside. The configuration will be in a written code or be in the configuration table as a XML type. So all configurations are fixed in build time for determinism. So far, we have explained the aviation standard and avionics information for developing the next story. So Gihwan will continue the story. Over to you.
As Haesun reviewed in the previous slides, the ARINC 653 standard defines critical requirements for avionics software partitioning. When we look at open source today, many of these critical partitioning features are either partially supported or missing altogether. For example, fully ARINC 653 compliant open source RTOS options are limited, and robust partition isolation and scheduling are often lacking. My hope is that through continued collaboration and innovation, the open source community will increasingly embrace and support these aviation-grade partitioning requirements. Doing so will unlock new opportunities for open source solutions to be safely and reliably adopted in the aerospace industry. To support ARINC 653, this kind of architecture is required. First and foremost, we need a certified hypervisor. The hypervisor must be capable of running multiple partitions and managing resources effectively. It should provide features such as modular scheduling, memory management, device management, virtual machine management, and health monitoring. Within each partition, a certified kernel is needed to manage the internal resources. For applications to run properly, the partition itself must be prepared to support process scheduling, error handling, and health monitoring. Additionally, to ensure robust applications, both inter-partition and intra-partition communication must be supported. We also believe that libraries should be provided to enable applications to operate using these features. To build such an architecture, we considered which open source software could be used. For the hypervisor, Zen or KVM would be suitable options as an open source. As for the kernel, of course, the Linux kernel would be the natural choice. For the C standard library and POSIX support, glibc and musl could be used. Out of requirements specified in ARINC 653, one of the major ones is temporal and spatial partitioning. In this presentation, I'll focus specifically on temporal partitioning. ARINC 653 defines a two-tiered scheduling approach to achieve deterministic scheduling. Partition scheduling is managed by the modular scheduler, and process scheduling within a single partition is managed by this process scheduler. To effectively support these schedulers, it is essential to fully understand the temporal partitioning requirements defined by ARINC 653. We'll explore this in more detail in the next slides. Let's begin with modular scheduling. Modular scheduling refers to the scheduling of partitions across cores. It defines when and for how long each partition is allowed to run within a fixed repeating cycle called the major time frame. The major time frame is divided into time windows, each assigned to a specific partition. The modular scheduler manages this schedule, ensuring that each partition gets its allocated CPU time in a deterministic and repeatable manner. As you can see in this diagram, the major time frame represents the fixed duration of a modular schedule, consists of three partitions, A, B, and C, which repeats continuously. Within the modular schedule, each partition's time window is defined by its offset and duration. A user can define configuration tables such as XML type. Build system shall parse all configuration data and apply to the system during build time. For determinism. Therefore, it cannot be changed during operation. However, depending on the operational mode, the system can switch between different module schedules by the privileged partitions, each of which is also predefined at build time. As I briefly mentioned earlier, within each partition's time window, multiple processes are managed by the process scheduler. It schedules processes based on rate monotonic scheduling policy. There are two types of processes, periodic and aperiodic. The diagram illustrates only the periodic processes running within the minor time frame. The key objective is to maintain a fixed period by executing periodic processes strictly for their defined duration, following a priority order from highest to lowest. While the Linux kernel offers various schedulers like RT, FIFO, and deadline, the rate monotonic scheduling by periodic process is crucial for meeting the temporal partitioning requirements specified in ARINC 653. Aperiodic processes, on the other hand, are triggered by external or internal events. So suppose we have a system running multiple applications, all assigned to run on a single core, core 1. I have defined the major time frame to be 10 milliseconds, and the applications run within their respective partitions during this time frame. For example, application 1 has an offset of 0 and a duration of 3 milliseconds. Application 2 starts at offset 3 milliseconds and run for 3 milliseconds, and so on. The system will repeatedly execute this major time frame during its operational mode, ensuring that each application runs periodically within its assigned partition. Let's take a closer look at the next tier. Suppose this system is running navigation software. The applications need to process sensor data while computing navigation solutions. Application 2 runs 2 periodic processes, one processing inertial measurement unit data, and the other processing GPS data. Let me explain how these processes are scheduled in this context. The IMU sensor data is processed for 1 millisecond, and the GPS data is processed for 2 milliseconds. Both processes run within application 2's partition time window, which lasts 3 milliseconds. The period of these processes are 10 milliseconds, as each process executes once every 10 milliseconds. A key point to remember is that rate monotonic scheduling policy is applied here. Since IMU data processing has a higher priority, it executes before GPS data processing. Additionally, each process runs for a fixed duration to ensure a fixed period. If rate monotonic scheduling policy was not applied, IMU sensing process finishing earlier or later could affect GPS controllers, period.
All right. As previously explained, ARINC 653 requires two-tier scheduling and requires specific features that an operating system must provide. For software already developed, such as open source software, there might be some gap between the existing software and the requirement of the standard. So these gaps must be analyzed, and how to fill them will be the future work. So I also want to briefly touch on the Boeing's collaboration with other open source communities. Right, in this diagram on the right, the area highlighted in yellow represent gaps in the ARINC 653 requirements compared to the status of the open source tools we are considering. So particularly relevant features include partition management, process management, and the health monitoring. So I will give an example in the next slide. Right. If we look at the Apex specification related to the process management, we see the phrase like the one in the middle. So the create process service request creates a process and returns an identifier. Based on the phrase alone, it seems like any process creation system call or the POSIX API provided by the Linux kernel would work. However, if we look at the attribute struct for the process creation, as you may recall, we need to specify a priority attribute for each process. And as you can see, the priority range is specified between 1 through 239. So 239 is the highest one. This is quite different from the RT priority or the nice value range provided by the Linux kernel. So there are a significant number of gaps like this, so we will need to do some research on to fill them. So last but not least, we've been collaborating with open source communities. We already are active as the chair of 2 working groups in the Linux Foundation ELISA. So the one is the aerospace working group, and another is tool investigation and code improvement working group. And furthermore, for muscle library, we contributed a test suite for the muscle API verification. And my team is particularly interested in the hypervisor-related things. So as they close align with the partitioning principles outlined in the Apex. So my team has already made several code contributions, and we plan to actively discuss certification artifacts as well. Right. Thank you for your time, and I hope this presentation was helpful for you, and I'm happy to take any question, even in Korean. Right?
Korean or English?
I'm okay with the Korean, but depends. Up to you.
저는 현대자동차에서 왔는데요. 저희 이제 자동차와 항공이 비슷한 고민을 하고 있고 하고 있는 분야인데 한 3가지 정도 질문이 있습니다. 일단 저희 자동차 쪽에서는 이미 하이퍼바이저를 적용해야 되고 멀티플 VM을 통해서 리얼타임 선택을 구현을 해서 이미 자동차에 채택이 되기 때문에 아까 파티션 개념을 VM이 아니라 컨테이너 컨셉으로 접근하는 생각은 그렇게 안 해보셨어요?
비슷한 컨셉을 생각하고 있는데 이제 컨테이너 같은 경우는 저희가 로버스니스 측면에서 이제 하이퍼바이저에 있는 VM 개념보다는 이제 좀 더 로우 레벨에 적용할 수 있는 방법이라고 생각은 하고 있는데 사실 그 방법에 대해서 결정을 짓지는 않았습니다.
하이퍼바이저 사용해서 양산을 해보면 생각보다 컴플렉시티가 높거든요. 많이 높아요. 두 번째 질문은 항공에서 가지고 있는 리얼타임 빅사이즈나 달 같은 세티 빅사이즈가 있을 텐데 리눅스의 프리엠프트 RT만으로 리얼타임 빅사이즈가 충분할까? 프리엠프터블 리눅스가 프로텍션 노가드에 대해서. 두 번째로는 달을 달성하는데 리눅스가 가능하신 건가?
일단 먼저 그 후자 질문에 대해서 답을 드리자면 사실 그거에 대한 저희가 뭐 결론을 얻지는 못했지만 저희가 그걸 달성하기 위한 일들을 지금 진행을 하고 있는 중이다. 여기까지만 말씀드릴 수 있을 것 같고 그다음에 프리엠프트 RT 관련해서도 저희는 같은 사실 고민을 하고 있고요. 근데 이제 프리엠프트 RT를 적용했을 때 디터미니즘 관점에서 달성할 수 있을지 여부는 리서치 중에 있습니다.
없는 것보다 훨씬 낫지만.
네. Any other question? Any other question?
So immediately your company is working on the Linux kernel process scheduling, particularly two-tier scheduling. Does it mean like the company is interested in actually contributing to the kernel patch, adding new process scheduler in the main line of the kernel? I mean, or does the company just want to develop its own Linux kernel?
I think that's our work now, but I couldn't say that we are working on that, and we might need to contribute the code in the kernel because maybe there might be some needs or actually as far as I know the open source community worried about the generic code contribution rather than the industry specific one. So that's one of the issue, and the other one is IP. Alright.
가상화에서 CPU 튜닝을 했을 때 어떤 세이프티 관련 요청이 있으신가요? 지금은 한 CPU에서 여러 개의 스케줄링을 했을 텐데 하나 CPU를 튜닝을 했다고 하면은 저런 요청이 완화되는 거죠?
제가 알기로는 일단 다른 벤더 오퍼레이팅 시스템을 저희가 레퍼런스 했을 때 CPU당 하나의 파티션을 할당하는 게 훨씬 로버스니스 관점이나 컴플렉시티 관점에서 더 쉽게 접근할 수 있는 방법이라고 생각하기 때문에 그걸 아예 리미테이션으로 두고 가이드하는 오퍼레이팅 시스템이 있고요. 저희 같은 경우는 아직 그 부분을 좀 고려를 해보고 있습니다.
오토모티브에서 쓰는 하이퍼바이저는 두 가지 모드를 다 지원을 해요, 통상적으로. 실제 양산 시에는 VM당 CPU를 한 대 이상을 피팅해서 스타일이긴 합니다. 그게 더 스케줄링 관점 용이합니다.
Any other questions?
템포럴 파티셔닝을 구현을 하는데 리눅스 커널만의 허실 형태로 완전히 구현하기 어려울 것 같은데 유저 스페이스에서 유저 구현을 해가지고 커널 스페이스에서 메시지 구현을 해야 될 것 같은데 그런 식으로 좀 구현을
일단 저희 하이퍼바이저를 쓰는 이유 중에 하나는 사실 유저 스페이스라기보다는 하이퍼바이저 상태 익셉션 레벨이랑 그다음에 커널 레벨을 분리하고자 하는 목적이지 유저 레벨은 사실 고려하지 않고 있거든요. 그래서
하이퍼바이저하고 커널만
네, 그렇게 하려고 하고 있습니다.
사실 IMA 구조가 ARINC 요참의 구조 자체로도 사실 만족을 하는데 굳이 두 가지 레이어, 그냥 커널하고 하이퍼바이저 두 레이어에서 다 지원하십니까?
그것은 아까 저 현대에서 오신 분이 질문한 내용이랑 비슷한 내용인데 사실 그 프로세스 커널 레벨에서 두 티어로 스케줄링을 지원하는 거는 가능한 걸로 알고 있습니다. 그렇지만 이제 로버스니스 측면에서 그게 VM을 쓰는 것보다 더 로버스니스가 있는가라는 측면에서 소프트웨어 레벨 A가 가장 높은 겁니다. 그래서 레벨 A까지 지원할 수 있을까 하는 부분에 있어서 저희는 더 로버스티니스한 구조를 가져가기 위해서 그 하이퍼바이저가 이제 아키텍처에 들어간 경우이고요. 그리고 앞에 이제 메모리, 그러니까 타임 말고 스페이셜 파티셔닝에 관해서는 사실 저희도 고려하고 있는 부분이 있는데 저희 이 슬롯의 시간상 다 말씀드리기가 어려워서 그 부분은 발표드리지 않았습니다. Right? We have 1 minute. No other questions. Thank you for being here. So.